Welcome to today's explainer. Let's just dive right into this because this blueprint of a TDA2040 single supply power amplifier is absolutely fascinating. We're going to trace the entire journey of an audio signal straight through this schematic. And to do that, we really have to start right at the source. Take a look at the bottom left. We're picking up the left and right channel outputs, labeled L and R, coming directly from the MP3 module. And notice how the very first things our audio signal hits are these two 10K resistors. This right here, this is exactly where our circuit story begins.
So, following that green line from the MP3 module's L and R outputs, you can actually see the stereo signal traveling right through those twin 10K resistors and physically converging. It turns into a single unified green line. Basically, we're taking two totally distinct paths of audio data and merging them together right out of the gate.
Before we get too deep into the weeds, let's just lay out the physical path. Step 1, MP3 module. Step 2, 10K resistor mix. Step 3, 50K potentiometer. Step 4, the TDA2040 IC itself. And Step 5, speaker output. All right, let's keep moving. Now you might be wondering, why on earth did we have to do that merge at Step 2? It's a stark contrast, right? The dual stereo output of the MP3 player versus the sheer physical necessity of creating a unified single mono line. Well, here's the deal. We're feeding a single channel TDA2040 amplifier. This chip only has one input for the audio. It literally cannot process a separate left and right channel at the same time. So mixing those signals down with those resistors, that isn't just some stylistic design choice, it is an absolute physical necessity to make this specific single chip setup actually work. Okay, so moving along, our newly mixed mono signal arrives directly at the left pin of that large blue 50K potentiometer sitting right there on the left side of the schematic. Let's break down exactly what's happening here. A 50K pot, or potentiometer, is essentially a three-terminal resistor with a sliding or rotating contact that forms an adjustable voltage divider. In everyday terms, it controls your volume. It's the physical gatekeeper of our circuit. But the way it works is pretty clever. It doesn't magically shrink the signal. Instead, it actually bleeds excess audio signals straight down to that black ground line you see right beneath it. Turn it down, and it dumps more signal to ground, letting only the exact volume you want slip through the center pin and head toward the amplifier core. Right, so from that center pin, the signal travels through a small 2.2 microfarad coupling capacitor. Think of this little guy as a sort of one-way toll booth. Once it passes through, it flows straight into pin 1 of our TDA2040 chip. That specific pin is the non-inverting input of the IC. The audio has officially arrived at the amplifier. But wait, here's where we hit a massive design challenge. And it's all because of what we're talking about today, a single supply configuration. So what does that actually mean? It means we are powering this entire amplifier using only a positive voltage, specifically plus 12 volts, and a ground line. No negative voltage supply whatsoever. Now here's the catch. Audio signals are AC. Their waveforms naturally swing positive and negative, kind of like waves on the ocean. If you feed an ocean wave into an amplifier that only has positive power, the entire bottom half of that wave gets instantly chopped off. The result? A crunchy, heavily distorted, basically unlistenable mess. To fix this, our audio signal desperately needs a DC offset, a bias voltage, to physically lift the whole audio waveform up into positive voltage territory. That way, it can swing up and down freely without clipping. And honestly, this brings us to one of the most elegant parts of the entire schematic. Look right at the input of pin 1. See those two 22K resistors sitting above and below the green input line? The top one hooks straight up to the red plus 12 volt power line. The bottom one drops straight down to the black ground line. Since they're identical 22K values, they create a flawless 50-50 voltage divider. They literally take that 12 volts, chop it exactly in half, and create a rock-steady 6 volt DC bias precisely at pin 1. It acts like an elevator, lifting our incoming audio signal to sit perfectly in the middle of our power supply. Boom, single supply problem solved instantly. Section 1, stabilizing the amplifier, the passive component network. Okay, check out the interaction here between pin 4 and pin 2. If you trace that long green line, it takes the output at pin 4, routes it back underneath, and feeds it right into the input at pin 2 through that 20K resistor. This right here, this is the absolutely critical feedback loop. It's essentially taking a tiny sample of the amplified output and feeding it right back into the inverting input. That loop is what sets the amplifier's overall gain. It dictates exactly how much louder the output is going to
to be compared to what went in.
Let's quickly break down the specific roles of this entire passive support cluster, because every single piece has a totally vital job. As we just saw, the 20K resistor sets up that feedback loop from pin 4 to pin 2. Working hand in hand with it are the 22 microfarad capacitor and the 680 ohm resistor, which connect pin 2 straight down to ground. Together, these guys determine the exact AC gain curve of the audio. And finally, look over to the right of that cluster. You've got a 4.7 ohm resistor and a red 104 capacitor bridging the output line to ground. This forms an RC network. See, amplifiers can sometimes get a little too eager and start generating these super fast, unstable, high-frequency oscillations. You can't hear them, but they will absolutely overheat and fry the chip. This RC network acts like a high-tech sponge, soaking up and stabilizing those nasty high-frequency spikes.
Moving up to the top right corner, we find the power supply block. You can see the green terminals where the raw plus 12-volt power actually enters the circuit. It travels beautifully along that top red line, diving straight into pin 5 of the IC, basically breathing life into the whole operation. But right next to those terminals, you literally cannot miss that massive 2,200 microfarad capacitor sitting right across the 12-volt red line and the black ground line. Why on earth is it so huge? Well, think of it like a giant energy reservoir. When your music hits a really heavy bass note, the amplifier suddenly demands a massive gulp of power. And that sudden draw can actually cause the voltage from your power supply to briefly sag or dip. So this giant capacitor stores up a ton of energy and just dumps it instantly during those heavy bass hits. It smooths out the voltage dips and makes sure the amplifier never ever starves for power.
We are officially on the final leg of the journey now. Follow that last green line exiting from pin 4. This right here is our fully amplified, robust audio signal. It pushes through one last component, the second large 2,200 microfarad output coupling capacitor, and makes a beeline straight for the positive terminal of the speaker.
Which actually brings us to a really fascinating question. Just look at the size of that thing. Why do we need to use a massive 2,200 microfarad capacitor sitting right in series with the speaker output? What is it actually doing there, right at the grand finale of our signal's journey?
Well, the answer brings this whole schematic full circle. Remember back at pin 1, where we created that clever 50-50 voltage divider to add a 6-volt DC bias? Well, that DC bias is hitchhiked all the way through the amplifier. If we were to send 6 volts of pure, continuous DC power directly into a super-sensitive speaker coil, it would physically push the speaker cone all the way out, lock it there, and eventually just melt the coil into a smoking ruin. No joke. So this final 2200 microfarad capacitor acts as a literal brick wall for direct current. It completely blocks that DC bias we added earlier, leaving it in the dust, while allowing only the dynamic, pure AC audio wave to safely pass through and drive the speaker. It's honestly just so cool to step back and look at the sheer elegance of a single supply design like this. We started with a basic MP3 stereo signal. Through physical necessity and just incredibly clever component placement, we merged it, biased it to survive on just 12 volts, bulletproofed it against self-destruction, gave it a localized power reservoir, and finally stripped away the bias voltage right before it hit the speaker. Every single passive component is working in perfect symphony here to transform a tiny little electrical flutter into a massive audio powerhouse. So if this intricate symphony of parts is what it takes just to amplify a single mono signal, imagine the hidden, staggering complexity inside the smartphone sitting in your pocket right now. What else are we plugging into every single day without even realizing the sheer engineering magic going on inside?